Hello and welcome back to the MoDyPy Basics tutorial series. In this tutorial, I will show you how to use multidimensional states to model a planet orbit. If you are the kind of person who rather reads tutorials instead of watching them, hop over to docs.modypy.org, where you will find this tutorial series in text form. In this tutorial, I will show you how to model a planet orbiting a sun. So far, we only had scalar states, but now we will need two-dimensional states to represent the x and y coordinate of position and velocity. But first, let's look into the physics. The planet that is orbiting the sun is drawn towards the sun by a force that is proportional to both the mass of the sun and the mass of the planet. So the acceleration with which it is drawn towards that sun is proportional to the mass of the sun. And let's write this down in vectorial form. Here we have the derivative of the velocity, which is the acceleration. And the absolute value of that vector, so the length of that vector, is the global gravitational constant times the mass of the sun divided by the distance squared. And to convert this into a vector that is pointing in the correct direction, we will take the position vector, which points from the sun towards the planet, divided by its length, so we get a unit vector, and then invert its direction. So now we have a unit vector that is pointing from the planet towards the sun. And this we multiply by the amount of acceleration. And of course, for the position, the derivative is simply the velocity. So here I already prepared a little bit. I already imported system and state classes from the model package. I also got our simulator and simulation result classes from the simulation package. We will be using norm to calculate the length of a vector, and we take that from the NumPy linear algebra package. And of course, we will use PLT from matplotlib to plot our results. I defined some of the constants because they are tedious to type. We have here the gravitational constant in meters cubed per second squared. And we have the sun's mass in kilogram. I also get some parameters of the Earth orbit, and as we are working in the SI system, this is in meter and meter per second. So we have the perihel, which is the distance closest to the sun, and we have the velocity while the Earth is in perihel. I also defined the rotation time, so the time used for one orbit. And based on that, we can define our initial state. So the position shall be in the perihel, and the velocity shall be that of the perihel point. And this negative sign ensures that our Earth is rotating the correct way around the sun. Now we define our system and our two states. The first state is the velocity. And its derivative function, which we will define in a second, is the velocity dt. Its shape is 2, which identifies a vector of dimension 2. You can define other shapes, such as matrices. For example, this would be a 3x3 matrix, or any other form of tensor by adding additional dimensions here. For us, the shape is 2 for a two-dimensional vector. And the initial value is V0. For the position, we do the same. Here, the derivative function is simply the velocity state. Its shape is also 2, and its initial condition is x0. Now we define the derivative function. And here we now have to deal with not only scalars and vectors, as we had previously for scalar states, where the scalar case was when we had just a single system state to consider, and the vector case was when we had multiple system states to consider. But now we have a multi-dimensional state. Let's get the position, which we will need later on for calculating the direction of our gravitational pull vector. Well, let's get the position from the system state. Now there are two cases. The case where we have one system state represented, so one time. Here, the shape of the position is 2, or 2 comma, the list with one entry. So what we can say here is just pos of 0 will be the x coordinate and pos of 1 will be the y coordinate. Let me put that here. Pos of y is the single y coordinate. The other case is we have multiple system states, multiple time instances. In that case, we have the shape of pos equal 2 comma k. And here k is the number of time instances. What does that mean for our array access? Pos of 0 will be a sequence of x coordinates. Shape is k. And pos y will be a sequence of y coordinates with a shape equaling k as well. So let's just think what would happen if we had a matrix. In that case, let's say we have a matrix of a state of shape 3 by 3. Then in case A, single time, we would have, let's call it M, the matrix state M. We have M of 0, 0, which would be a single entry, a single scalar. In case B, where we have multiple times, M0 of 0 would be a vector or a sequence of values of M0, 0 over time. So M0, 0, K would be the value of M0, 0 at time instance k. What does that mean for us? It means that the dimensions of the state itself are always the first dimensions, and the dimension that represents the time instance is always the last index. So for us, this means our length or our distance is the norm of the position, but we must take care that only the sum over the first axis is calculated. So we have, in the case of multiple positions, we have distance of 0 equal the square root of position of 0, 0 squared plus position 0, 1, 0 squared. And the distance of k is then exactly that, just with the index k. If we wouldn't specify that, we would just get distance as the square root of position 0, 0 squared plus position 0, 1 squared plus position 1, 0 squared, and so on. And that would be a single scalar, and we don't want that. We want for each position the distance. And for that, we specify the axis here. And now what we return is minus g times the sun's mass divided by the distance cubed times the position. Actually, we could write it that way, but it's a little bit quicker to write it this way. And that already defines our system completely. So now we want to do a simulation. We start at time 0, and I will specify a step time, maximum step time of a day. We'll get our result here. And we will run for a complete rotation. And now if we want to plot the trajectory, so we want to have on the x-axis the x-coordinate and on the y-axis the y-coordinate, we get our trajectory from the result. So this now is a vector of form or shape 2, k. So trajectory 0 is the sequence of x coordinates, and trajectory y, 1, is the sequence of y coordinates. And that means we can now simply say plot trajectory 0, trajectory 1, and we will set the aspect ratio of the output so that it is square. And then show the plot. What we see here is a circle, pretty much. And although the Earth runs in an ellipse around the Sun, that ellipse has such a low eccentricity that we won't see it with the naked eye in such a representation. What we can do, however, is plot the distance over time. So we calculate the distance using the norm again. And again using the axis equals 0 argument here. And we plot that over time. And we create a new figure for that so that we have a new window. And here we see the distance changing over time. And we see that there is a noticeable change. So we do have an ellipse here, but it's only in the, or mainly in the second significant digit after the decimal. So it's no wonder that we don't see it here in this very coarse representation. So that's it for multiple dimensions and states. A similar thing is possible with signals. When you have the signal function decorator and you define some signal, for example, returning the cosine and sine as a vector over time. And you can say signal function shape equals 2, so that is a two-dimensional signal. And that is important because MoDyPy does some sanity checks when you connect signals together and ensures that they have the same shape, or there are some helper functions that create, for example, an integrator from a signal, and they need to know how big the integrator state needs to be. And by looking into the shape of the signal, they can determine that. So that's it for this tutorial. And there's still much more to come, so I hope to see you again. Bye bye.